So in this screencast, I will run through the practical exercises associated with the Snowball Earth carbonate silicate weathering model exercise that we did in week 2 in the Earth Life module this year. So you can download the question sheet from Blackboard under Friday workshops. And you can also download the model code, which you can run in RStudio as we did in the practical. But I've now also uploaded a version of the model to the cloud, to shinyapps.io. So if you go to martwine.shinyapps.io/whackprack, you'll be able to run it for free via the web. Hopefully that'll fix some of the problems that we had with Greek symbols not rendering. So for instance, these sigmas here look like capital I's with umlauts on top and strange things like that. So we'll run through question by question through the question sheet. So if you remember, first page of the question sheet just explained how to get the model up and running. That should now be quite simple. The reason that this interactive model was developed was to replace some of the numerical exercises that previously ran in the module, where students would sit with pen and paper and calculator and plug and chug through the same equations to derive different states of the Earth system in terms of temperature and energy balance through a Snowball Earth event. So a whole practical got us through a Snowball Earth, whereas now we can cover energy balance, Snowball Earth, and carbonate silicate weathering feedback in one session, and the model also allows us to go on to investigate biological enhancement of weathering and volcanism, which was done in week 4. So the underlying maths and the equation derivations are great and useful for you to understand, but more important is that you understand the mechanisms underlying them. Hopefully that's what the second half of the session did. So the first question is regarding constructing an equation that allows us to figure out whatever the solar constant value was, or the incoming solar radiation was at any point through time, given that we know the starting and finishing incoming radiation and how long the Earth has been here. So you're told that in the present day the incoming radiation is 1365 watts per meter squared, and at the beginning it was 955. So and then it says, remember that the equation for a straight line is y equals mx plus c. So y and x are coordinates on the y and x axis, c is the intercept, and m is the gradient. So the first thing to do is to calculate the gradient. So you can do that by the difference between 955 and 1365. So that gives you the gradient, divided by 4.6 billion years to give you the gradient. So that's watts per meter squared per billion years. And so there are some challenges around time is negative, so how do we get the equation to start in the right place and finish in the right place? And you can twiddle positive and negative values around to get that, but eventually you can arrive at an equation that is numerically equivalent to s equals minus 89.78 times t plus 1368. So t is the time in billions of years, and it doesn't have a negative on it because the negative sign is here. So if we just run a number in there, if we do 89 times, let's say 1 billion year ago, so 89 times 1 is still 89, or 89.78. So that's negative 89.78 plus 1368. So effectively it's 1368 minus about 90. If you look there, 1368 minus about 90 is 1278, which looks like about the right value. So that's the equation that defines the change in incoming solar radiation through time, and that's at the core of the model. Because if you remember, if you think back to when we did this, ran this model in the practical, one of the sliders, which we'll see again later as I run through it, is it controls the time, because the time controls the solar incoming radiation and therefore changes the state of the system. So that's question 1. Question 2 is concerned with deriving the energy balance equation. So the first question asks us to write down an expression for the total amount of solar energy absorbed by the Earth in terms of the solar constant, the planetary albedo, and Earth's radius r. So in the guidance and the question sheet it says, imagine what the Earth looks like to the Sun. If you hold a sphere up, then all you see is a disk. So the area of the Earth over which the Sun's energy is absorbed looks like a disk of radius r, where that's the radius of the Earth. So we can express then the amount of incoming solar radiation captured by the Earth as this solar incoming radiation S times pi r squared, which is the area of a circle. However, a proportion of that incoming radiation is reflected back out due to the reflectivity of the Earth, which is expressed through the albedo. So the albedo is the fraction that is reflected, so 1 minus the albedo is the fraction that is absorbed. So the answer to A is S 1 minus A times pi r squared. And then part B says write down a second expression for the total amount of energy emitted by the planet in terms of emissions temperature, Stefan's constant, and R. So if we look over here, it tells us that the energy emitted by the planet, assuming that it's a black body emitting infrared radiation, is sigma TE to the 4. That has no area component. That's just it's per meter squared. So we need to know how many meters squared it's emitted over. Now it's not emitted over just that disk that captures the incoming solar radiation. It's emitted over the whole of the sphere of the planet. So the surface area of a sphere is 4 pi r squared. So we can then multiply this term here by 4 pi r squared to give the amount emitted. So that's sigma TE to the 4 times 4 pi r squared. Now, at steady state, we know that the amount of energy coming in is equal to the amount of energy going out. So we can put those two terms either side of an equal sign. So that's saying S 1 minus A times pi r squared equals 4 sigma TE to the 4 times pi r squared. So the pi r squareds cancel, and then we can simplify and rearrange the equation down to this term for the emission temperature. So this tells us the temperature of the Earth if there was no greenhouse effect, and it's a function of the incoming solar radiation, the albedo, and Stefan's constant. And this is important because it's a key component of the model, the equations that underlie the model that we use in the rest of the practical. So, going back to the energy balance model, we see that this effective temperature changes through time as a function of the solar constant. We've seen that the solar constant changes through time. So, therefore, we can take a look at how the effective temperature, the emission temperature, changes through time. And the key thing to take from this is that it's pretty cold. This is the snow line, so that's 273 Kelvin. So when the average temperature of the planet is 273 Kelvin, it's effectively frozen over. And so the effective temperature on its own is way below that. So the question here says experiment with albedo values to see if you can warm things up a bit. How do you get it, or what value of albedo is needed to get the black line, which is the temperature of the planet's surface above the temperature at which it would have frozen. So if we ramp up the albedo, then the value is going down because more is being reflected. So let's ramp the albedo down. Let's bring it down to, say, 0.25, 0.2. So even at 0.2, we haven't managed to get a warm enough temperature at any point through Earth history. Go to 0.1, maybe that will make a difference. Oh, that's 0.11. So we're still below freezing throughout Earth history. So we need to go down to an albedo of maybe 0.08 or 0.07 to get the temperature over the threshold for unfreezing the snowball Earth, if you like. So that's not a realistic value of albedo. We know the present day albedo is roughly 0.31 or 0.32, and there's no evidence to suggest that it was significantly different in the past. So something's missing from this model. It doesn't really do what we want it to do, which is predict something that looks vaguely realistic in terms of global temperature. So question B down here is what key property of our atmosphere is missing from this model? And of course the answer is the greenhouse effect, which is on the next tab. So the greenhouse effect, if we go back to the question sheet, we can see that Earth's surface temperature can be represented by the effective temperature, which we were just discussing, and then the temperature added on to that from each of a series of greenhouse gases, which traps outgoing infrared radiation. So the one we're really interested in for now is CO2. Methane, we won't really concern ourselves with, or the details of the greenhouse effect, but it's important to realise that these CO2 formulations of the greenhouse effect that we're looking at in this section of the practical integrate implicitly the water vapour greenhouse, or at least the change in the and the change in the water vapour greenhouse with temperature. So there's a bit of simplification of the system. So these formulations use a kind of CO2 relative to the present, or at least the pre-industrial, so PAL, it's called present atmospheric level, but really it's normally the reference level is normally actually the pre-industrial level, so before we started emitting carbon from fossil fuels and increasing the CO2 concentration. And so both the Walker-Hazen casting model and the other model represent surface temperature as a function of CO2 concentration. Now the one that Walker-Hazen casting use has a effective temperature at a fixed value. We can change that to be variable. The GCM one, or the one derived from the GCM, explicitly gives the effective temperature down here. So this one changes through time by default as the solar constant changes and the effective temperature changes. So the key thing from this to take from this part of the exercise is that different greenhouse models look quite different. You'd think we'd understand this. You would think we would understand this really, really well, as it's a key part of climate science. Actually, for the present day and the kind of variability that we're looking at over the next few hundred years, it's probably pretty well constrained. But then if we're looking at the long-term variability, things are a bit more challenging. So how might CO2 greenhouse effect change when instead of looking at between 1 and 10 times present atmospheric level, we're looking at up to 100 times present atmospheric level. So it's this part of the curve that's less certain. So this is Walker-Hazen casting's CO2 function. If we plot this one, we've got the greenhouse derived from the GCM. So the form is similar, but the details are different. And in the practical sheet, it says have a go at tuning the parameter values for the WACC function for the Walker-Hazen casting model until it's close to that of the GCM one. So that's just a bit of fun, really, to show that you can twiddle the knobs of any model to get the result that you might want. Although, of course, the resulting model may in no way be physically realistic as a result of that extreme tuning. So these models are different because of the conceptual basis on which they are derived, and therefore they give different results, not only because their parameter values are different, but because the underlying assumptions behind them are different. So, question C asks, at what CO2 concentration is the surface temperature most sensitive to a change in CO2 concentration, and why? And so you can see from the shape of the plot, whichever of these models that you look at for the CO2 greenhouse, that the largest change in temperature with CO2 is at low CO2, at zero CO2, because that's when this line is steepest and most vertical. The reason for that is that the first bit of CO2 you put into the atmosphere is most effective. When you've got loads there already, most of the heat is already being trapped. So the effect of adding another bit of CO2 is relatively marginal up here. And you see that actually the difference between this GCM-derived function and the Walker-Hazen-Casting function is that the CO2 sensitivity at higher concentrations of CO2 is greater in the WACC model, and actually that probably makes a big difference to the predicted value of CO2 back in the early Earth. So then part D is calculate the climate sensitivity of the two greenhouse models. Now, the climate sensitivity is the temperature change for a doubling of CO2. So we can use this part of the interface down here to do that calculation. So if we look with CO2 at 1 times present atmospheric level, Walker-Hazen-Casting CO2 greenhouse function, we have a temperature of 285. So if we increase that to 2, then that updates to 286.3. So the sensitivity of the climate sensitivity of that greenhouse function is about 1.3 degrees C. If we now look at the other model, notice they don't start at exactly the same value. Increase that to 2, we go from 287.2 to 290.2, so that has a climate sensitivity of 3. So that's considerably higher, but off the top of my head, the recent IPCC report suggested a climate sensitivity of between about 1.4 and about 3.2, I believe. So the more modern GCM-based formulation is certainly within that range. The Walker-Hazen-Casting one is a bit below the lower end probably, but not a million miles away. So neither of them seem completely unreasonable for climate sensitivity at the present day. However, climate sensitivity changes as the CO2 changes. So if we look at the next doubling, we go from 286.3 up to 288. So that's a 1.7. So the climate sensitivity appears to have increased in the second doubling. So it changes. That climate sensitivity isn't a fixed function of the system. Okay, so that is the relationship between CO2 and temperature. The key thing about the carbonate silicate weathering feedback is that there's another component to the system, which is the effect of temperature on CO2. And so that's what we see in the fifth slide of this interactive model. So where we were looking at CO2 versus temperature, so that's this plot here, we saw the CO2 function, or the CO2 greenhouse function, had a shape something like that. This plot here then, and this is with the axes the other way round, is the reverse of that. It's the effect of temperature on CO2 through weathering. So this is derived by Walker-Hazen-Casting by looking at weathering rates and their relationship to temperature based on present day estimates. So as the temperature increases, the CO2 concentration decreases because weathering is temperature dependent. And so as temperature increases, CO2 drawdown increases, and the equilibrium CO2 concentration decreases. So what we have here is two simultaneous equations describing the interactions between temperature and CO2. So the greenhouse forcing is the effect of CO2 on temperature, and the weathering effect is the effect of temperature on CO2. If you remember from other parts of the course, where we've looked at simultaneous equations, we see that the stable, steady state solution to those simultaneous equations is the point of the intersection of the lines, if you like. So let's have a look at that greenhouse function. If we plot the greenhouse function, nothing happens, or apparently nothing happens, and that's because the albedo isn't quite right. And we need to tune the albedo so that our energy balance greenhouse effect model that predicts temperature as a function of CO2 is in the right place for the present day, which is having a CO2 present atmospheric level of 1, pre-industrial level. So if we increase the albedo, when we get to see the CO2 value is changing here as a result of us twiddling the albedo. So at this point we have CO2 of 1, and it's the point at which the lines intersect at a temperature of 285 Kelvin, which is roughly present day. So these functions are highly simplified and imperfect, so it's an approximation. So now what we see, or now what we can see when we follow part D, run the model back through time and see what happens to CO2. Why is this? So if there were no interaction between temperature and weathering, running the model back through time, we would simply end up, if CO2 stayed at 1 times present atmospheric level, we would just see the temperature plummet down to a much, much lower level, but that's not actually what happens. So if we run this back a little bit, let's go to 500 million years ago, then we see the CO2 has increased to 2 times present atmospheric level. The solar constant has decreased, the effective temperature has decreased, the CO2 concentration has increased, which has mediated the temperature change considerably. So instead of being about 281, it's actually about 282.1. And the reason for that is that where the effective temperature is lower, the weathering rate for a given CO2 concentration is lower, and therefore CO2 at equilibrium will accumulate in the atmosphere relative to a higher solar constant. There will be more CO2 in the atmosphere. So we're running back through time, and as you see, you can see visually that the intersection point, which is the solution of the two simultaneous equations of the effect of CO2 on temperature and the effect of temperature on CO2, is moving up. Oh, sorry, that's the wrong way. Is moving up the pink line. So where the effective temperature was lower because of the lower solar constant, CO2 was higher, and that's going some of the way to mitigate, or considerable way to mitigate, this temperature change. So the temperature at 3 billion years ago, without the carbonate silicate weathering feedback leading to a higher CO2 concentration in the atmosphere, the temperature would be minus 20 or something like that. Sorry, yes, minus 30. So very cold, the Earth would be completely frozen over. Actually, as it is, with these two functions, it still looks like the Earth would have been frozen over. So we can see that these functions don't explain the faint young sun paradox in their entirety, but you can see that there is a mechanism here by which CO2 can be higher in the past due to this interaction between weathering and CO2 greenhouse. So, those previous sections give you the background to the equations that are in the model that underlies this bit of software. So, that's the model that you can now control from this set of interfaces here. So we have time, which controls the solar constant and therefore the effective temperature. And within the model, when this box is ticked here, we solve temperature and CO2 on the basis of running to carbonate silicate equilibrium. We can change the albedo, we can add in a bit of methane greenhouse warming so that we can run through some of these experiments here. So let's have a look at those. So we can easily add a bit of methane greenhouse in here, so we can just add 2 degrees of greenhouse warming. As a result of that, let's just take a look at what happens. If we add in a bit of methane, then the CO2 concentration goes down. Why is that? Well, adding in methane is a bit like increasing the solar constant. It increases the weathering rate for a given CO2 concentration and therefore brings CO2 and temperature down. So, part B points out that this doesn't look quite right. So at 2.3 billion years ago, we know that the Earth was in a habitable state, and yet the temperature here is below or very close to that would lead to a snowball. Depends on what you have your albedo set to as to exactly what temperature you get in the solution to the model here. But we suspect it was quite a lot warmer than that. So a good way to solve that, and there are a number of different options, but a good way to set that is to reduce the weathering to approximately half of what it was today, on the basis that we didn't have land plants at this time in Earth history, and therefore if there's any biological enhancement of weathering, it might be between a factor of 2 and 10. So if we reduce the weathering rate, then we get some kind of realistic looking temperature, potentially chilly, but not frozen over. This highlights the huge uncertainties there are in the models, the equations that go in to make up this model. So these are really poorly constrained, and the idea of the Walker-Hazen-Casting analysis and of this practical is to highlight the potential processes rather than give numerical solutions to, for instance, what the global temperature was 2.3 billion years ago. So 2.3 billion years ago, before the Great Oxidation, we also know that, or there is lots of evidence to suggest that there were considerable methane concentrations in the atmosphere. So at the end of the Archean, so there's the paper by Hack-Misra et al. That we looked at in one of the lectures. So, if we whack up methane warming to 10 degrees Celsius, then the temperature hasn't quite increased by 10, because the CO2 concentration has gone down because of the response to the carbonate silicate weathering feedback. So here we are, it's just before the Great Oxidation event. There's lots of methane in the atmosphere. As a result, there's not lots of CO2 in the atmosphere. So now we look at what happens when that methane is very rapidly used up by the flip of the atmosphere to being oxygen dominated, and all of that methane gets volatilized away. So that happens much, much quicker than carbonate silicate weathering equilibrium. That weathering equilibrium happens on a timescale of hundreds of thousands to millions of years, whereas the methane might all be gone in a few decades or even less. So if we turn off this carbonate silicate weathering, turn off that steady state, we can look at the response of the system to taking that methane out. So keep an eye on CO2 and temperature here as we ramp the methane down. So methane goes down. Just let the calculations catch up. Now CO2 isn't changing because carbonate silicate weathering isn't responding over this time scale. This is just a bit of atmospheric chemistry taking the methane out of the atmosphere. So CO2 stayed constant. Temperature has plunged by 20 degrees Kelvin. We're now in a snowball state. Because we're in a snowball state, albedo has gone up. Because the Earth's covered in ice. So the albedo is now 0.65. And look, the temperature is really very cold indeed. So the next question, or the end of that question, by what process does the planet escape this state of being completely frozen over? Obviously this is the accumulation of CO2 in the atmosphere from volcanoes. So in order to build up the CO2 in the model, we need to hit this button here. Now what this does in the background is it solves the equations for a temperature of 260K. So it increases CO2 until it hits a temperature of 260K effectively. So that's what we do here. Temperature's gone up to 260K at the albedo given. We've got 2069 times the pre-industrial level of CO2 is required to get to that threshold at which you start melting at the equator, and therefore you can have runaway feedback to rapidly melt the ice. The ice is melted, so the albedo returns to 0.32. We need, of course, to deselect build up CO2 Snowball breakout temperature. And there you see then CO2 is 2069 times pre-industrial level. With the albedo down at 0.32, we've gone from 260 Kelvin to 334 Kelvin, which is extremely hot. It's a super greenhouse. So what mechanism rights the system, brings the system back into equilibrium? That's the next question, part H. And of course the answer to that is carbonate silicate weathering. So if we turn the carbonate silicate weathering back on, then it will solve the system for methane of 0, albedo 0.32 at the solar incoming radiation and effective temperature of 2.3 billion years ago. So here we go, and we come down to 45.9 times present atmospheric level at a temperature not that different to how we were when we started before we added those 10 degrees of methane. In fact, exactly the same. So, there we are. We've been through the Great Oxidation event. The methane being rapidly removed led to a deep glaciation that was escaped by the buildup of CO2, the melting of the ice, and then carbonate silicate weathering, righting the system back to long-term equilibrium value. And that's the end of the first practical that we looked at using this model. So hopefully this has been useful information. Thanks for listening.